Hello everyone, welcome back to the channel. We are doing Leetcode 1922, count good numbers, which also happens to be the problem of the day for today. It says a digit string is good if the digits 0 indexed at even indices are even. So the numbers which are at even indices are even and the numbers which are at odd indices are prime, 2, 3, 5, 7. Now 11 is also a prime number, but then they are talking about single digits. Okay, so in single digits only these four numbers are prime. For example, 2, 5, 8, 2. So if I talk about the even indices, 2 and 8, even numbers, odd indices, 5 and 2, odd numbers, right? It's good because the digits 2 and 8 are even and 5 and 2 are odd. Sorry, at odd positions are prime. If I talk about 3, 2, 4, 5, then 3 is at an even index, but it's not an even number, right? So that's why this is not a good number. Given an integer n, return the total number of good digit strings of length n. Okay, and since the answer may be very large, return it modulo 10 to the power 9 plus 7. A digit string is a string consisting of digits 0 through 9 that may contain leading zeros. Okay, so the constraint over here you can see if 10 to the power 15. Okay, so this lets us know, देखो, this lets us know that we cannot do this in linear time complexity. But if still, first of all, we are going to consider what the linear time complexity approach is going to be. Okay, now if I take any screenshot of the problem statement and paste it over at my 1450, we'll remember this. So okay, so I paste it over here, and the examples were 1, 4 and 50, right? These three different examples we had. If you think about it, if I have a 4-digit number, okay, and I want to make a good number, so at 0 index, 1 index, 2 index, 3 index, at 0 index, how many choices do I have? I can choose any one of these numbers, right? 0, 2, 4, 6, 8. So I have 5 choices over here. Similarly, I have 5 choices over here. But for the odd indices, how many choices do I have? I have 4 choices. Why? Because 2, 3, 5 or 7, right? How many prime numbers do I have? 2, 3, 5 and 7. So if I multiply all of these numbers, 5 into 4 into 5 into 4, what do I get? I get 400, which was actually the answer for this particular test case, right? So the easiest approach would be that you calculate how many odd indices there are. There are 2 odd indices. How many even indices there are? There are 2 even indices, right? After doing that, what you can do is the simplest approach would be that you run a for loop 2 times and do 5 into 5, and then you run a for loop 2 times and you do 5 into 5. But then if you already know that you have 5 2 times, sorry, 4 4, if you already know that you have 5 2 times, why are you doing 5 into 5? Why can't you just do 5 into 2 in one operation, right? Or 4 into 2 in one operation? But again, behind the scenes, how do we calculate the power? Isn't it 5 into 5, right? Or for example, if I had to calculate 5 to the power 16, if I had a very large number that had 16, let's say, even indices and 16 odd indices, so I would have to calculate 5 to the power 16 into 4 to the power 16, isn't it? Now the problem which we face is I can very easily calculate 5 to the power 16 by multiplying 5 with itself 16 times, right? That is what, if a to the power b is the general form, then that is an o to the o of b solution, right? Can I do anything which is better than linear time complexity when I'm calculating the power of any base number? Yes, I can, and that is binary exponentiation. I just made the video for this. The video tutorial, it includes concepts like what is binary exponentiation, why do we need it, what advantage does it give us. So if you see that video, you will be able to very easily solve this problem by your own, right? So I'm not going to repeat what binary exponentiation is, but we are going to use the very same formula in order to solve this problem. Okay, How that looks like is, I'll just give you a very simple example. I've already covered it in a separate video where we dived deep into what binary exponentiation is. But rather than calculating 5 to the power 16 as multiplying 5 16 times, you can calculate it like this: 5 to the power 8 whole square. Then you can calculate 5 to the power 8 as 5 to the power 4 whole square. You can calculate 5 to the power 4 as 5 to the power 2 whole square. 5 to the power 2 is just 5 to the power 1 whole square. Now 5 to the power 1 is just 5. So 5 square becomes equals to 25. 25 square becomes equals to uh, whatever 25 square is. So that comes over here. Then this goes over here. This goes over. This basically lets you know what 5 to the power 16 is going to be. So rather than 16 operations, all you did were 4 operations. So you're going from O of B to O of log B, isn't it? So you're going from a linear time complexity to a logarithmic time complexity, and it's a very exponential gain. It's a, you can't even think about it. Just think about when when you're taking 40 operations over here, you're taking 2 to the power 40 operations over here, and 2 to the power 40 is like 1,000 billion, probably something like that. 100 billion is less, 1,000 billion, or it's going to be even greater than that. So it's a very, 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 very large gain that we have. Now, how do we do binary exponentiation? That's very simple. We are going to use fast exponentiation, also known as binary exponentiation, in order to solve this problem. How? Dekho, I already know for any given number, how many even indices are going to be there. For example, uh, if n is 4, let's say, if n is 4 if n is 4, then I had 2 even, 2 odd. But then if n was 5, I would have had 0, 2 and 4. I would have had 3 even and 2 odd. Okay, so I can very simply do something like this. So 5 plus 1 divided by 2, number of even numbers. Similarly, over here I would have done 4 plus 1 divided by 2, which gives me 2 even numbers. Over here it gives me 3 even numbers. And in order to calculate the odd indices, what I can do, I can just do, over here I had 4 digits, so 4 divided by 2 gives me 2 odd digits, and over here 5 divided by 2 gives me 2 odd digits, right? So that is very easily how we can calculate how many, this many even numbers I will need. So I will calculate 5 to the power n plus 1 divided by 2, because I need 5 those many times. And similarly, how many times do I need 4? I need 4 n by 2 times. And then just like they said, return it modulo 10 to the power 9 plus 7. I'm going to make sure that I do that as well. How the solve function is going to look like is very simple. First of all, what we do is, I don't know about what a to the power b is, but I can calculate a to the power b by 2. Isn't this what we were doing? I don't know what 5 to the power 16 is, but I can calculate what 5 to the power 8 is going to be. Then 5 to the power 4, 5 to the power 2, and ultimately our base case, which is 5 to the power 1. Right. So over here I calculate what 5 to the power 8 is, and then I square it. After squaring, I'm going to check if b was odd. If b was odd, then I would have to multiply. Dekho, I'll give you, I'll explain what this means. If it was 5 to the power 17, then I would have had to do 5 to the power 8 whole square 2 into 5 to the power 1, right? So that 5 to the power 16 into 5 to the power 1 becomes 5 into 17. So for odd powers, when b is odd, I need to have this check in place. Okay. Similarly, I'm just going to return half. And then what was the base case? That when you can do something like this as well. If b is equals to 1, then just return whatever a was. If I submit this code, let's see if it passes all the test cases. It doesn't. Why does it not? Maybe let's go with the previous thing, see if it passes all the test cases. Oh no, it does. So what was wrong? What's wrong if I do something like this? If I do that when b is equals to 1, return a. What's wrong with this? um when n is 1, when n is 1, so what, that will lead to an infinite recursion, right? Because when n is 1, I will say over here 1 divided by 2, so it would be 4 to the power 0, and 0 is something which I'm not dealing. That's why I need to have this test case in over here, right? This was the only simple test case that was failing. That's why our code wasn't accepting. So rather than including both of the test cases, that when b is equal 0 and then when b is equal 1, you can just go with it, right? This is going to get accepted. So I hope now you have a very good idea of how count good numbers was being solved by the concept of binary exponentiation, and I would highly recommend that you solve another question which is of the same concept as well, and that is Leetcode 50 power of x to the power n, right? Do solve this question as well. It, you can just copy paste the solution over here. It is built up of the same concept, and it would be a very good practice for you on how you can use binary exponentiation in order to solve different problems. Okay, I hope you found the video helpful, and I'll see you in the next one.